We're now going to hear from Dr. Brendon. Dr. Boot is a neurologist in the Division of Cognitive and Behavioral Neurology at Brigham and Women's Hospital, Boston. Dr. Boot investigates clinical and genetic contributions to the causes of Alzheimer's disease, dementia with Lewy bodies, and Parkinson's disease as well. And Dr. Boot will speak to us about early diagnosis and treatment of the disease. Dr. Boot.
I'm going to start with a question for you all. There's a professor in the UK called Clive Ballard who did a bit of research in some of the nursing homes over there. He got people to be observed for 6 hours during the day in that nursing home, those who had dementia. But I want you to guess how many minutes, on average, people had one-on-one, face-to-face contact. Shut up, please.
15 minutes.
4. 4 minutes every 6 hours, I think, would be a drain on all of us. So I really want to commend the people in this program for what they do. I'm also going to start with some advice for those who are considering a medical career. Make sure you find... I'm going to pick this up. Okay, just go on. Is that better? So, if you do decide to do medicine, make sure you find a disease where you love the patients and you hate the disease. And this is a good one. I'm also here to ask for your help. We are looking for people to volunteer with us in any of these age groups, 55 to 90, those who don't have memory problems, those who do have memory problems, those who've got mild ones, if you have family members, loved ones. We have all kinds of research with people who, some of them are short, some of them are very long, and all of them are interesting. So please, if you're interested, you can search, ask Mrs. Google the words Alzheimer's and Brigham. It will be the first thing that comes up. It's the Centre for Alzheimer's Research and Treatment. The scholastic philosophers used to ask this question. They debated for decades. And they came up with their own answers. I'm going to give you mine. Underneath, oh, by the way, this is a pinhead if you can't see very well. Underneath every bit of cortex, even the size of a pin, you have many, many neurons. And each of these neurons has a cell body and it has these little wires, these are connections that go. And those connections are incredibly complex. They connect one nerve to the other. And at the other end of that wire is a bunch of little branches. So these are quite short ones here of the nerve cell. The little wires lead up these tiny little branches. And each nerve cell connects to tens of thousands, if not more, other nerve cells. And it's with those that you are you. It's with the complexity of those that you are able to form new memories by making new joins, new synapses. And by thinking, it's merely the pattern of those connections that makes you think. So if we take the cortex and we unfold it, it's all folded on itself, you come up that yay big, about the size of a New York Times. Now if you take a piece of that cortex, the size of a pinhead, underneath that pinhead, there is this many neurons, 1.2 billion. Impressive, but that's just the start. Each of those neurons connects to, or could connect to, this number of other neurons. It's even more complex than that, because a thought isn't just a connection, a thought is the dynamic pattern of each of these nerves talking to each other. So there is enough connections for there for you to process more than there are atoms in the known universe. So it's these things that make you you, make you complex, make you beautiful. And it's when you lose these that you become demented. Alzheimer's is the most common form of dementia, and let's talk about that a bit. Firstly, we're not talking about normal aging, or on the top here. We've got bad news for you. If you're over 30, you're on a downhill slope. The good news is, most of you are going to be here. You're just going to have a mild change. But what is it about people that suddenly take this terrible decline? Well, there's a few things. You've heard about them. Let's start that video for me. So, there's two major proteins that are involved, and one of them you've heard about, so both of them you've heard about already. amyloid and tau. So we're going to go through, as we go, I don't know if we've got that to work just yet. Anyway, we'll start a kind of fly through the brain. You'll see some nerve cells. I think if you just click actually on, it should work. Anyway, we're going to go fly through the brain, and you'll see various nerve cells and these wires I was telling you about, and firing of neurons one to the other. And what happens is 10, 20, perhaps 30 years before somebody develops the symptoms of Alzheimer's disease, they start to collect this first protein called amyloid. And amyloid collects and is pushed outside of the cells, and if it's there for long enough, then eventually that interferes with the cell's ability to look after itself. And you see this kind of dying back of the nerve cells. Now, there's this problem. This amyloid is actually a normal part of the brain, but the way that it is cut up is abnormal in Alzheimer's disease. So it ends up in this tiny little sticky fragment that you'll see coming up. And that sticky fragment collects outside the cells. You can see them dying back here. And eventually you end up over here, these kind of buttery collections over here. Here's another one. This is the amyloid plaque. And the second is these dead cells that collect this second protein called tau. So the amyloid plaques develop first, probably. And then the tau tangles are a late change due to cell death. So this is how you form the amyloid. You have on the cell surface of every neuron this protein that gets cut up by these two enzymes. And it's the wrong combination of these enzymes. And produced are these little fragments of beta amyloid. The bad thing about those is they're really sticky. One sticks to the other, sticks to the other. All of a sudden you have these big long fibers. Those fibers collect together and they form these big, nasty plaques. The other thing about this is that pretty much all of us, as we get old enough, will have these. But only some of us get affected. The second protein, we've gone inside that wire of the cell, and this is an information superhighway that runs all the way up and down the length of that nerve. And tau is that little scaffolding bit there you see. And this is a transporter. This is what's happening inside your nerve cells now, is our transporters can taking nutrients down one end of the cell and bringing back all of the rubbish the other way. If that superhighway breaks down, the tangles form because that scaffolding, the tau, is also sticky. It sticks together, and all of a sudden there's a mess of that, and it stops the cell being able to survive. The cell dies back, and there you have a tau tangle. When you have those two together, then you have the cell death that you see later in the disease. And as the brain gets older and older, it shrinks and shrinks until you have this this shrunken brain, particularly in the memory parts of the brain down the bottom there. So they're the two processes: amyloid plaques and tau tangles. So what I'm not going to talk to you about in treatment terms is, before we get on there, another idea of just what kind of scale we're at here. This is actually a photograph of tau. This is a scanning electron micrograph of a tau protein. These are small. Here's our pinhead again. If I wanted to cover just with one layer of that pinhead, I wanted to cover the top of this pinhead, I would need 5 billion of them. This is a small protein. So, how can we treat this disease? There's many different ways. I'm going to talk to you about one particular approach, which has the most promise. What I'm not going to talk to you about are those symptomatic treatments that you've probably heard of: Aricept, Razodime, Exelon, Namenda. They're just symptomatic treatments. They don't really help the disease in terms of its progression. They're valuable boosts to someone's thinking once they have the disease. They don't arrest it. What I'm going to talk to you about is this idea: stopping this in its tracks, or even turning it the other way. Here's the good news. There's good news, there's bad news coming to you. The good news is that treatments work. They work at hitting the target with this amyloid. Now, this is the most common way. You have an antibody that you inject in the body, it binds onto the amyloid and pulls it out of the brain. And that we know happens. That's seen in humans. Here we have a couple of PET scans. Here's a person who's normal on the top. There's an amyloid PET scan. This is someone with Alzheimer's disease. More or less how this works, it's another antibody. It's bound with some radioactivity. You inject it, it goes into the brain, and we measure the radioactivity. And these are kind of horizontal chops through into this brain. You can see the person in our body here has a lot more. But going back here, what I haven't put up here is some evidence to show that after we give someone these treatments, we can reduce the amount of this amyloid that we see on these PET scans. We're getting rid of it. We're getting rid of that over a matter of months to years. But this is the problem. Even though we can do that, these people still decline in memory. We don't change the trajectory of their memory loss. Why is that? Well, there's two possible reasons. One is amyloid has nothing to do with it, and we've gone down the wrong track. I think that's incorrect, and I think just about everybody else in the field, so save a few, agrees. What do we think is happening? We think that down here, someone has lost so many of their nerve cells that no matter how good your treatment is, no matter how effective it is, there's no way you can treat a dead nerve cell. What we need to do is find people back here, before they've lost those nerve cells, before they've gone down this track. And we're talking 10, 20, 30 years before someone might be diagnosed with dementia. Can we do that? Yes, we can. We can do this already. We have the technology here at Massachusetts General. So here again, same kind of PET scans, someone who's normal, someone with Alzheimer's disease, nice and warm colours, well not nice, but warm colours. Here's someone who is cognitively normal who also has the warm colours. This is someone who has preclinical Alzheimer's disease. The same data over here, this is the Alzheimer's disease group, and you can see they have lots of amyloid. The mild cognitive impairment, which is an intermediate stage, a lot of them do too. But look in the normal group, there's a substantial proportion of them in their 50s and 60s who have a positive scan. And our group is going to lead a national study screening 10,000 people in their 50s and 60s to identify these people, give them these treatments, and hopefully save their neurons. I'm going to finish by one more request from you. If anyone's interested in those studies or any other studies, we have many different kinds of studies. We would love to hear from you. Alzheimer's and Brigham, and your finders. Thank you.